welcome to the House of ZK Radio, which is a focused podcast and media channel exploring everything ZK, zero knowledge. Hi everyone, my name is Alice. I am the primary host of House of ZK Radio. I'm joined here today with Leo, who is co-founder of Cysic. Very excited to have you here today, Leo.
Thanks for inviting me.
Yeah, of course.
Yeah, I'm very happy to be here.
Yeah, so am I. Wondering if we can first start off with an introduction. So how did you get involved in the Web3 and ZK spaces, and then also how you got focused specifically within the hardware acceleration?
Okay, yeah, so I can do a little bit background intro about me. My name is Leo Fan. I got my PhD in cryptography from Cornell. So in 2019, and I spent 4 years in Ithaca, New York. And before Cornell, I did about 4 years Bitcoin mining in China, Bitcoin mining and other altcoin mining in China. So after Cornell, then I spent some time at NIST, which is doing this post-quantum crypto standardization process, and then in Agrant, where when I was at Agrant, I helped design and also implement. There's a primitive called Agrant state proof, which is essentially is a ZK bridge, can be bridge Agrant Ethereum, Agrant Solana. So at that time, I found the proof generation time for the ZK bridge takes so much time. I try to think probably we can borrow some idea from my previous Bitcoin mining experience to say we can have some hardware to accelerate the proof generation for that. So that's why we started doing Cysic and in the hardware acceleration space. Yeah.
Mm-hmm. Yes, yeah, and I think it's really important for projects to realize that in order to improve the proof generation time, it's not just from the software side, but it also comes from hardware as well.
Right.
Yeah, and just on that topic, I'm wondering if you can give an overview of the current solutions today in terms of accelerating hardware. So we see CPU-based, GPU-based, ASIC-based. Can you speak about the differences between those kinds of solutions?
Yeah, sure, yeah. So I'll start with the most easiest one, since it's not yet here. Yeah, the easiest one is using ASIC to do the ZK proving. Is you basically can achieve real-time proving. By real-time, you can generate all the ZK proofs. I think for the current ZK circuit in less than 5 seconds. So that's for the ASIC. But the ASIC is not there yet. Yeah, since the go-to-market time for ASIC takes a very long time. Basically you need to do a lot of engineering, and then you work with an external team to do some back engineering, and then we send all the materials to TSMC or this fabs to do the chip tape out. And this is a very time-consuming, also capital-intensive game. Yeah, so it's not there yet. Yeah. But before that, you can always try to use the GPU and FPGA to do the proof acceleration. Yeah, so Cysic starts doing FPGA acceleration. So we have this Sonar product, Sonar MS and Sonar NTT, which is quite performant, I think. But even if you accelerate, I guess certain parts of the ZK proof generation, the whole end-to-end proof generation time is still quite, I guess, the speed up is quite limited, probably 2 to 3 times speed up. And also FPGA is very hard to write the code for FPGA, and you also need to get a lot of FPGAs to do the proving, which is quite hard. Yeah, I'm not sure why, but you cannot buy a lot of FPGA online. You need to talk to some AMD dealer to get that. So that's why we shift from the FPGA engineering to GPU. Mm-hmm. So the GPU, I guess, is right now the majority of the proving resource for the ZK community. So it's the speed up is still quite limited, from probably 3 to 5 times speed up compared with the CPU. But you can get a lot of GPUs, and previously in Ethereum mining, in Filecoin mining, there are a lot of GPU just sitting idle there. So you can reuse this GPU to do the ZK proof generation for our customers. Yeah.
Okay, nice. Yeah, very good to see kind of all of the trade-offs that exist within them, and then also the thinking that goes behind why you guys
Yeah.
like transitioned from FPGA to GPU based.
Mm-hmm.
Wondering when we're looking in the future, do you see one approach dominating over the other? Like you mentioned that ASIC right now may be too early, but do you see one particular method becoming more prevalent, or do you see maybe a combination of these different choices being used at the same time? What are your predictions for the future in terms of the hardware?
Yeah, so like the like one, I guess, like one major difference between the ZK proving and the Bitcoin mining is like there are like just so many ZK algorithms right now. The people haven't converged to say like which algorithm will be like standard, or like which algorithm will like dominate the space.
Mm-hmm.
Yeah, if there is like a lot of variety in the space, probably like I guess like ASIC will still take a major part of the market, but there will be still like GPU there to proving some like algorithms that's not covered by the ASICs, and also like there are like more algorithms coming to the space, and probably like GPUs can be used to do the ZK proving for the like newly algorithms, while like ASICs will be used to do some like major ZK proving part. Yeah, so that's my like understanding about that. And the Cysic is will like ship our hardware product. I mean the ASIC based product to the market in 2025. Yeah.
2025 coming
Yeah.
soon. Okay, that's very exciting. Yeah,
Yeah.
nice. And just wondering on the real-time proving point that you previously talked about.
Mhm.
When we're building towards that stage, once we reach it, what new applications will we see? What will real-time proving enable for developers, for people using ZK?
Okay, yeah. So I guess like one simple example here is like in Vitalik's poster, he mentioned like they probably like want to snarkify the whole Ethereum layer one.
Mm-hmm.
And if you want to snarkify the whole Ethereum layer one, like there is like a very wide tree called the Merkle-Patria tree, and so it contains a lot of hash function there. And the real-time proving allow us, like the ASIC enabled real-time proving allow us to prove these like hash functions, like I guess like more than 500,000 hash functions per second. And right now you can only prove say probably like 10,000 hash functions per second. So that's not enough to snarkify the Ethereum layer one. But if you have the ASICs, which you can prove like 500,000 hash function per second, then you can snarkify Ethereum. So you can satisfy Vitalik's requirement about the Verge approach. Yeah, so that's like one simple example. Another one is to say like there is a very nice combination of ZK and AI. It's called like the ZK ML. So basically, like the scenario is something like this. Like you want to use a specific AI model to do some inference on your data, and probably like the server is lazy or it want to save some money, so it will use a like much simpler AI model. Say if you want to use like GPT-4, but they use like GPT-2 to do the inference. And from humans' perspective, actually you cannot tell the difference between the results like from like GPT-2 or GPT-3 and from like GPT-4. So the solution here is to say like you can always attach a ZK proof, the ZK certificate, to the inference result to say like we are actually using this like specific model you mentioned to do the inference for you. Yeah, so that's like one scenario of like how to use like ZK to enable like more trustful like AI. But right now it's like, as you know, the AI model is very, very complicated. It's like much more complicated than all the circuit like we encounter in the layer 2s, like the ZK bridge or the other applications. So if you use like GPU to do the proving, it takes about like days or probably like hours or even days to do the proving. But using like ASICs, you can probably like do it in seconds. Like yeah, hopefully we can achieve the ZK proving for this large AI model in about 10 or 5 seconds. So it will enable a more widely used of like ZK-ML. Yeah.
I see. So for both, say, snarkifying Ethereum and then also with enabling ZK-ML, most likely those ASIC-based solutions will be able to achieve quicker proving than, say, GPU-based.
Right.
Okay, I see. Yeah. Nice. And I'm also wondering, in terms of the accessibility side, what sort of challenges or limitations come with, say, like client-side ZK proving on the hardware side? What's preventing ZK from reaching more mainstream adoption? And are there any sort of opportunities that you see on the hardware side that could improve that adoption standpoint?
Yeah, so like if we have like better hardware and this hardware are accessible to our like customers, probably like they can just buy it online.
Mm-hmm.
It may enable a lot of like use cases for using the ZK technology. So for here, yeah, we are like also talking to Cisco, like to say like to have like our hardware chip in their switch machine. Yeah, since like if you use like a VPN to visit some website, all the traffic will be like encrypted or like invisible to other people, and yeah, but you still want to maintain the compliance requirement of that. So you can use ZK to do that. So that's like if you have a like faster enough like ZK hardware that's like embedded into the switch machine from say Cisco or some other manufacturers, then it will like be used to prove all the network traffic satisfy the compliance. So that's probably like more connected to the traditional world, I think.
Mm-hmm. I see. Yeah, and hopefully we'll see this become more consumer-based, where consumers can directly buy hardware to enable that ZK proving, and it's not just, say, reserved to like certain companies or like certain people, but we're sort of diversifying accessibility in that way. Hopefully we can reach that stage sometime soon.
Yeah, so like the Cysic, we have like several hardware products, and one of them is called like ZK Air. So it's basically the size of a MacBook charger, and you can connect it the ZK Air to your cell phone, to your laptop via the Type-C connection. So it's very convenient for people to use, like to do some client-side proving, and like you can basically use it using this like piece of hardware to satisfy some like KYC requirement. Yeah, so for the KYC, the bank or some other commercial institution, they do not need to know exactly your information. They just want to make sure you satisfy their KYC requirement, and then you can use ZK Air to do some like client-side proving to prove that you satisfy the KYC, but without leaking any specific information about yourself.
Mm-hmm. Yeah, and it's pretty incredible to think that for the Air product in general, it's the size of a MacBook charger, and that can directly be connected to your laptop, to your phone for proving. So I see that being applied a lot to increasing accessibility here, because anyone can really do that. Most people have like MacBooks and also iPhones, so they could like very easily do that. So pretty exciting. Also wondering if you could talk a bit more about hardware optimization. So for our proof systems today, are there specific proof systems that may be more optimized for this hardware, or any kinds of specific hardware optimizations for these proof systems that need to be done? What makes a solution hardware friendly?
Okay, so this is a tough question here. So like we cannot influence too much on our like customers. By customer, I mean like this ZK project. Since it's a ZK project, the big ZK project, they develop the necessary proving backend, the software part. So like we just want to like satisfy our customers' needs. Like we develop some like hardware acceleration for them to use. Like I guess like it also depends on the hardware. Like if you are doing like GPU engineering, probably like the integer-based operation are better for you. If you are doing some like the bitwise operation, probably like you can try the FPGA or ASICs. Yeah, but actually like we cannot influence too much on the like how the proof backends they like evolve. Yeah. Probably like after we have some like very promising ZK hardware, like that's like faster enough, cheap enough for people to use, then there will maybe a trend like people this like ZK projects they will like migrate to our like hardware. They will just tweak their technologies to suit like our hardware requirements. Yeah.
I see. And just on the topic for also ZKVMs, are there specific kinds of considerations or optimizations that projects who are building ZKVMs should consider? A lot of ZKVMs, like for example today, use continuation, so splitting a program into different segments, and then potentially those segments could be proven in parallel for different hardware. So I'm wondering if there's any sort of optimizations that you see ZKVMs or even other kind of ZK projects should focus on to make it more optimized for the hardware.
Okay, yeah. So actually, like our hardware design was like inspired by the ZKVM. So previously, like we are doing the Hello 2 proving, like we do some acceleration for that. And one challenge there is to say, although like you can accelerate the MS entity or polynomial evaluation to the extreme, but as I said before, the speed up compared with the CPU is still quite limited, at least 3 or 5 times. And the reason for that is like there is another like special component in the ZK proof generation part called the program synthesizing. And the program synthesizing, first of all, it's like takes a lot of time, and second, it's like I guess it will become different like for every possible ZK circuit. So you need to design some like hardware that's like powerful enough and also genuine enough to support this component, which like from Cysic perspective is very hard to do that. Yeah, since we are just a startup, we have a very limited budget to do the thing. So that's why like we probably like sometime last year, I guess the middle of last year, we saw a lot of like progress in the ZKVM part. And so the ZKVM, like one nice part of ZKVM is that their circuit is fixed. It's basically the CPU execution circuit. And if something is fixed, then you can put it on your hardware like very easily. Like you do not need to be as generous enough. You just need to be as powerful as enough. So that's like one nice property of the KVM. The second property, as you mentioned, is the continuation part. Like you basically, after the CPU executes the VM, it will dump like a trace of that, like probably like also a sequence of operations on the ZKVM, and you just divide it into like smaller segments, and then you use a lot of like from our perspective, a lot of like ALU calls to do the proving for each segment, and also because of that, the segment actually will be the data transmission will be way much smaller than doing it for the previous approach, the Hello 2 or like Plunky 2, Plunky 3 approach. Yeah, so the data transmission will be also like much smaller than before, which will also increase a lot on the speed up, since like data transmission also accounts for like a very large portion of the ZK proof generation.
Yeah, and besides data transmission, within that ZK proof generation process, what other steps take a very long time? Like for example, MSMs, the NTT step. I know that for that particular, it takes quite a big portion for that proof generation process. But are there any specific stages in the proof generation that does take quite a bit or does have some performance challenges attached?
Yeah, so like I'll first explain like why this MS entity takes so much time. Like for MSM, it's like it's like about the multi-scalar multiplication, and you are dealing with the curves. And the curves, like for each point, is like about 256 bits long, and you are doing it for 2 to the 20 or even up to that. Like you basically need to calculate that a very large number. Yeah, so it's 2 to the 20, and each bit, each like coordinate is about 256 bits. So it's a very large calculation there, and you also need to transmit the data from like your memory to your ALU cores. So that's like one part that takes a lot of time. And MSN NDT, so that's in the curve-based ZK proof generation. And second, there is this like hash-based proof system, like such as the Fry. So Fry, like you can have like Plunky 2 or Plunky 3 of Fry, like just different implementations. For Fry, like you need to open like a Merkle tree path. The opening also takes a lot of time. And so we are just talking about the back end. On the front end, where the program synthesizing is happening, it also basically you like for the Fry-based one, you have, or for the Plunk-based one, you have a very large table to fill in, and for each entry of the table is like also a 64-bit or 256-bit integers. So a lot of like computation and data transmission like you need to do in the ZK proof generation part, which is why it's like takes a lot of time.
I see. So there's quite a few different stages in that process that all contribute to the high proof generation time.
Yeah.
Okay, I see. Yeah, and I'm also wondering if we could talk a little bit more about like Cysic's network. You previously mentioned some of the products that you guys offer on the hardware side, but I'm also curious to hear more about the components of the network. So maybe you could speak about first the architectural components and then also the participants in that network and what their roles are. I know that there's like agents, validator committees, as well as provers, and how they all contribute to the network.
Okay, yeah. So Cysic network is a layer 1 blockchain, and it's built based on Cosmos CDK. We can treat it as a ZK proof layer. So like in Cysic network, we attract a lot of like provers, verifiers to join Cysic network to do the ZK proof generation, ZK proof verification for our customers. So we bring it online, I think, 3 months ago in the end of July this year. So like in the past several months, we have already generated, I guess, more than 7 million proof for the whole ZK community. So for like each proof, for each like proof task, we select a bunch of like provers to do the proof generation, and we will award the first 2 provers to for their job. And after a proof is generated, we then select a bunch of like verifiers to verify the proof, and we also award the first 6 of the verifiers who verify the proof first. And we just use the layer 1 blockchain, the transaction in layer 1 blockchain, to keep track of the status of a proof. So a proof can have this like initiate, waiting for proof, waiting for verification, and then success. So those are like just the 4 status of a proof, and we use a blockchain to keep track of that. And also we store the proof. We store the hash of the proof in the blockchain. So that's for the how some like basic info on that. And why this like ZK projects they want to work with us is like we can basically prove like we much better proving speed at I guess like also like very reasonable cost. Yeah, so like for instance, like for like recently joined customer, if they want to like prove it on CPU, it takes about like 3 or 4 times than we do it on our GPU. Yeah, since like we also do a lot of like CUDA engineering to make sure like our performance is competitive in the space, and we charge less than they pay to like AWS or GCP. Yeah, so that's for the proving part, and for the verification, probably like in the upcoming weeks, we will have this like phone-based verification application, where like you can verify a ZK proof on a cell phone, and probably like you can also verify a ZK proof in a Telegram mini app. Yeah, so and the reason why we can do that is like we hugely reduce the data requirement on your cell phone. Like previously, like if you want to verify a ZK proof, like you need to download say 4 gigabytes of data as a setup to verify this. But after a lot of optimization, we reduce the data requirement from 4 gigabytes to I guess like 320 bytes. So that's a huge like Yeah, and because of that, you can have it on your cell phone. So on your cell phone or on like Telegram mini app will bring like more customer, bring on board more individuals to Cysic network.
Yeah, nice, and very incredible to see how we've come from like proofs only being able to generate on very specialized hardware to now potentially being able to generate on cell phones as well. So that kind of transition, I think, is quite incredible. And just wondering on the prover side of the network, I know you guys have decentralized the provers. So I'm wondering if you can talk about the implications of that prover decentralization and how those tasks are able to be delegated to different provers, how that works specifically with Cysic.
Okay, sure, yeah. So right now in testnet phase 1 is like permission provers. Like we still need to make sure the performance we deliver to our customers satisfy their requirements. So it's like permission provers. But in the upcoming testnet phase 2, I guess we will have this like permissionless prover to join. And yeah, so like in testnet phase 1, which is right now, is like we do the assignment, the proof task assignment in a very synchronized way. Yeah, since we just want to make sure like our performance satisfy the requirement. But in the upcoming phase 2, we will have this like more decentralized way to make sure like each prover know which task he's assigned to. So. And to be like more specific, so each like prover will run like a VRF. So it's a verifiable random function to determine whether this prover is eligible to participate in the ZK proof generation for this task. And if they are eligible to do that, then they can compete with some probably like some other eligible provers for the reward of the task. And the reward is like distributed in Cysic credits. So like we get paid by this like ZK projects, either via the stablecoin or like their tokens. But we pay our provers or verifier for their work using like the Cysic credits. At least for now, probably like in the future it will be like Cysic tokens. So we basically this like credit or tokens will incentivize like people to join Cysic network, since like their GPU are idle for quite a while and they just want to join Cysic network to participate in the ZK community, to actually doing some real computation there. Yeah, it's not like some like AI project you basically just plug in and your machine still idle there. But for Cysic network, if you join Cysic network, you can always get some real computation ongoing.
I see. So first for eligibility, the VRF is run, and then from there,
you compete
to get it. Okay, got it. Nice. And also wondering if you can speak a little bit about the consensus design that you guys are using. So I know that you guys have adopted the proof of compute consensus design. So I'm wondering just the reasons for the intention of designing this particular consensus design and how that compares to other options today.
Okay, yeah. So the consensus is like we have this like proof of compute. So the proof of compute is basically a combination of proof of work and proof of stake. It's designed to incentivize like more provers to join Cysic network. Since like after they do some like computation for Cysic network, they will get some like VE tokens. Like if you are doing some like proof generation for score, then you are getting some like VE score. If like for ADO, you are getting some like VE ADO, and this token is like a one-time use token. So after you get some of the token and you want to participate in the consensus process, so you can delegate your VE tokens to the validators. The validators will have like a certain number of like Cysic tokens staked to be like validators. But if you do not have the Cysic token, you can always delegate your like these VE tokens, which is like a reward to you for your computation contribution to Cysic network. And then like for each epoch, well, like epoch contains about like 100 blocks. For each epoch, like you can get some reward for participating in the consensus process. Yeah, it's like your like reward will be like proportional to like how much like you stake to you delegate or like stake to the validators. So so you are basically earning like multiple rewards, either like via this like V score like or Cysic token by being the verifier or being the prover of our network. Yeah.
Okay, so there's a couple of different roles, like both the prover and then also the verifier that you can take on. Okay, I see. Yeah, nice. And also wondering on the integration side for at least the hardware that Cysic will offer, what kinds of projects are able to integrate into the hardware? So besides like ZK rollups and perhaps ZK VMs, what's the main target user that you guys are looking at?
So right now, I guess the main paying customer are all these like ZK layer 2s. Yeah. So and for we still have a bunch of like smaller ZK projects which are still paying us to do the proof generation. Yeah, but the main part is the ZK layer 2s, and there is like we will publish some like smart contract API to make sure like previously it's still like it's like permissioned agent like, or if they want to use Cysic servers like there will be some integration part. And but in the upcoming like Cysic network phase 2, we will just publish the smart contract API. If you want to use like Cysic's ZK proof generation servers, you can just have a deploy this like deploy the task to a Cysic network. Of course, with some deposit to make sure like our work is like get paid. Yeah, so it will be like way much easier to use Cysic network to do the ZK proof generation, ZK proof verification in phase 2.
I see. Got it.
Yeah.
And just going back to, say, like the overarching vision for how you imagine the space to be, what in your opinion or in your view, what does the end game look like for ZK hardware acceleration? As in, when we reach that point, what applications will we enable? What would it look like?
Yeah, I guess if we have a hardware, like if the community have a hardware that's powerful enough and also cheap enough, then the community will converge probably like into using say like one or two ZK algorithms, and which will be like better for us since like you can always like just accelerate one algorithm instead of right now like 4 or 5, and at that time it will converge and the ASIC will take the majority of the market, but still there will be like room for GPU to do the proving. And then at that time, of course, we can snarkify Ethereum, and we can have this like ZKML running very fast. You know, when like you do not need to wait for hours or even days for the ZK certificate. You can have the certificate touched to your results as soon as possible, probably like just right after you submit your request. Yeah, so and I guess there will be like more consumer-based ZK applications such as like ZK passport. You do not need to upload your passport. Like for now, if you want to participate in DevCon and you are like in the local community, you need to upload your passport to somewhere, which is crazy. Yeah, so you just need to do some like client-side proving. Then use like probably like a ZK Air to generate a ZK proof of your passport, showing that you are like from the local community to get a huge discount in the ticket. Yeah, so I could imagine there will be like more consumer-based application of ZK with like this convenient hardware. Yeah.
Yeah, very excited also to see that consumer-based applications and even those that may be applicable like beyond Web3 natives, but people beyond the ecosystem or beyond the space that can utilize ZK hardware acceleration, especially for privacy-based applications.
Right,
so very excited, a very exciting future to come. And just as a last question before we close today's session, do you have any advice that you'd like to give to the audience or any announcements that you'd like to make on the Cysic side?
So like we will probably like bring the Cysic network phase 2 in the coming week, and then after probably like before that we will like also post some blog post to see how well like our hardware perform like in this like key check hash function. And our the hardware will be like probably like available for people to buy sometime next year in Q3 or Q4 next year.
Oh, very soon. That's
Yeah,
coming up very soon. Nice. And thank you so much, Leo, for all the insights today. I really enjoyed hearing about, especially how you talked about the trade-offs between the different acceleration methods, like FPGA, like with ASIC, GPU, and really liked also the insights you gave into what this can enable in the future, especially for use cases. And also pretty excited to see you guys come to market with the ZKR as well, coming up very soon. So thank you so much for being here today.
Thank you for inviting me. Yeah, it's a very nice chat. Yeah.
Yeah, thank you so much.
Thank you.
Thank you.